The observation that quantum measurements do not yield the same results when repeated under identical conditions is a fundamental characteristic of quantum mechanics, and it's known as the indeterminacy or uncertainty principle. This principle is a key feature of the probabilistic nature of quantum theory and is encapsulated in Heisenberg's uncertainty principle. Heisenberg's uncertainty principle states that there is a fundamental limit to how precisely we can simultaneously know certain pairs of properties, such as position and momentum, of a quantum particle. In other words, if you know the position of a particle with high precision, its momentum becomes highly uncertain, and vice versa. This inherent uncertainty in the properties of quantum particles means that you cannot predict their exact behavior with certainty. Here's why quantum measurements are inherently probabilistic. Wave-particle duality. Quantum particles, such as electrons and photons, exhibit both particle-like and wave-like properties. This duality means that their behavior is described by probability distributions rather than deterministic trajectories. When you measure the position or momentum of a quantum particle, the outcome is not a definite value, but rather a probability distribution of possible values. Superposition. Quantum particles can exist in a superposition of multiple states simultaneously. For example, an electron in an atom can be in a superposition of different energy levels. When you measure the electron's energy, it collapses into one of the allowed energy levels, and the outcome is probabilistic. Observer. Effect. The act of measurement itself can disturb the quantum system being measured. This is known as the observer effect. When you try to measure a quantum property with high precision, you necessarily change the state of the system, making it impossible to simultaneously know certain pairs of properties accurately. Entanglement. In quantum entanglement, particles become correlated in such a way that the measurement of one particle's property instantly influences the state of the other, even if they are separated by large distances. This leads to non-local and seemingly random behavior in measurements. Because of these principles, quantum mechanics predicts that when you perform the same measurement on a quantum system many times, you will obtain a range of different outcomes, each with a certain probability associated with it. This inherent randomness at the quantum level is a fundamental feature of the quantum world and stands in contrast to classical physics, where outcomes are deterministic. It's important to note that this inherent probabilistic nature of quantum mechanics does not imply that the theory is incomplete or incorrect. In fact, quantum mechanics has been incredibly successful in explaining and predicting the behavior of particles and systems at the quantum level. The probabilistic nature is a fundamental aspect of the quantum world.